Hello, multivariable calculus students. This is Mr. Johnson, and we're going to start section 11.6, which is on the directional derivative and the gradient vector. So up to this point, we've had a point on a surface, and we've calculated the rate of change in the direction of positive x, which is represented here, and we've calculated the rate of change in the positive y, which is represented here. So obviously we have two different rates that we're able to calculate, but it's pretty minimal compared to if you think of a surface and a point on a surface, the rate in any direction. And so we want to be able to calculate that. For example, if we look at our diagram here on the right, if we have a point on the surface and we want to calculate the rate in a direction other than positive x or positive y, so for example, the rate of change along this line on the touching the surface there, we want to be able to calculate the rate of change in a different direction, and we call that the directional derivative. What we need for that is a unit vector, which is represented as AB, in the desired direction. So again, this is a unit vector, and it's in the direction of AB, but occasionally what we want is the components of the unit vector in the angle form. So I'm just going to draw a quick little diagram here next to it. If this is our unit vector, and let's say that we have A and B, and for whatever reason we don't know what A or B is, but we do know what the angle is, then instead of writing our unit vector in terms of components A and B, we could write it in terms of cosine theta and sine theta simply by trig identities and the fact that the vector has a length of 1. Okay, now if you think about this, we've already basically calculated our derivatives that we know based on the directional derivative formula that you see below. So really quickly, the directional derivative formula is often represented d sub unit vector u of the function f of xy. And what we do is we take the partial derivative with respect to x, multiply by a, and the partial derivative with respect to y, and multiply by b, and then we add those up. So in other words, we're calculating based on the direction we want to go, which is the unit vector u, and the partial derivatives in each direction that we've already analyzed, and we sort of put everything together and we get the directional derivative that is in the direction of u based on the surface itself. Now, if you think back to when we did the partial derivative with respect to x and the slope that we analyzed in regard to that derivative, that would be if u was the vector 1, 0. So the unit vector 1, 0 would point in the direction of positive x, but it would not point at all in a different direction like positive y. It would just point along the positive x. And our formula that we have here, I'm going to erase these two parts that I highlighted. Our formula, if that's the case, means that this is gone, and we are simply left with the directional derivative f sub x, and then multiply by 1, of course. And that's really what we've calculated with regard to the rate of change in the positive x direction. And then obviously, if you were to look at the opposite case, so let me erase this, we have a unit vector 0, 1. And if that's the case, think about what's happening to our directional derivative formula. We would end up canceling this part of it because a is 0, and the directional derivative itself would be equal to the partial with respect to y. And so again, we've calculated these already with regard to just the rate of change in the positive x, the rate of change in the positive y. Now we're sort of putting them together in order to have a more usable derivative, and that is the derivative in any particular direction. So let me show you our first example, and you can see that we have a surface that is depicted in our picture over here, and then we have this plane, and this plane ends up slicing through the surface, and it gives us a direction that we're focused on. That direction is the vector u right here, and it has an angle of pi over 6 from the value parallel to the positive x axis. So in other words, we want to know what is the directional derivative based on the particular surface, and u is the unit vector given by this particular angle. Again, that's off of the positive x axis, and it wants us to calculate the derivative at 1, 2. So our first task is to find a unit vector that is pointing in the correct direction. We know the angle is pi over 6, but we need the components of this particular vector. So we have cosine of pi over 6 and sine of pi over 6, and that would give us square root 3 over 2 and then 1/2. We also need our partial derivatives, so we need the partial derivative with respect to x, which is 3x squared minus 3y, and the partial derivative with respect to y, which is going to be negative 3x plus 8y. And so for our directional derivative, we want to put all of this together. I'm going to write it just in general first. So we have the partial derivative in terms of x and y, which is going to be the quantity 3x squared minus 3y multiplied by the square root of 3 over 2 plus negative 3x plus 8y quantity multiplied by 1/2. So you can see that as we're looking at each of the parts, this is the partial derivative with respect to x, this is our partial derivative with respect to y, and then we have our value a and our value b. And so we put all of those items together based on our formula above. Okay. Now let's go ahead and plug in our final values for the directional derivative. So we want the directional derivative specifically at the point 1, 2. And so when we substitute that in, we get negative 3 multiplied by square root of 3 over 2 plus 13 multiplied by 1/2. And this one's a little bit ugly, so let's just leave this as 13 minus 3 root 3 over 2. And that is the slope in the direction of the vector u. Okay, let's look at the next page. Okay, in example 2, we're going to do the same thing. We just have a different problem, so it's just a good practice, but it is the same concept, nothing new here, except the function's a little bit different and the angle's a little bit different. So our first task is to calculate the vector u, which is cosine of pi over 4 and sine of pi over 4. And that's going to give us the square root of 2 over 2 and then the square root of 2 over 2. So we have our unit vector, we have our direction, and then we want to calculate the partial derivative. So the partial with respect to x, which is 2x y cubed, and then we have our partial with respect to y, which is 3x squared y squared minus 4y cubed. Now we want to calculate both of these partial derivatives at the point 2, 1, so let's go ahead and do that. For this one, we end up getting 4, and then for our partial with respect to y, we get 8. All right, let's put it all together. So our directional derivative at the point 2, 1 is going to be 4 multiplied by the square root of 2 over 2 plus 8 multiplied by the square root of 2 over 2. And that gives us 2 square root 2 plus 4 square root 2, and we get a total of 6 root 2. That's going to be our slope in the direction of u along that particular surface. Okay, so that's our first step. So can we calculate the directional derivative given a point on a surface as well as an angle that we want to analyze the slope in terms of a direction? Okay, the next part is on the gradient vector, and this is a really important concept that we end up using a lot in the future sections here. The gradient vector is written here below, and I'm going to try to explain kind of what the impact of this has on the directional derivative itself. But keep in mind, and this is where our textbook, it's a little bit confusing because they use a bold technique in order to communicate a vector. So the vector itself here is actually your symbol here in front of f. So the vector for the gradient is actually a vector made up of partial derivatives. So your components are simply partial derivatives of whatever function you're analyzing. And we're going to find that this actually could continue. You could have multiple partial derivatives based on the gradient. So the gradient could be any level of component, I guess you could say. In this case, we're just looking at a 2-component gradient vector, but this is my gradient vector, okay? All right, I'm going to go back up for a minute. So remember how we had our directional derivative of f of x, y, and the formula was the partial of f times a plus the partial of y times b. I'm just going to break that into the dot product between two vectors. So if you think about it for a second, the first vector would be f of x and f of y dotted with the vector a, b. And if we think about the formation of this dot product, that first vector, fx, fy, is actually the gradient vector f, and we're dotting it with the unit vector that is the direction we're trying to analyze. So the directional derivative is actually the product of a dot product calculation between the gradient vector and the unit vector. Now, there's actually a little bit more to this that I want to try to explain, and that is connected back to chapter 9 and the projection formula that we had for the component of two vectors being projected onto themselves. So if you think back to chapter 9, we had, for example, some vector. We're going to call it the gradient vector in this case, because that's the one we're analyzing. And another vector, we're going to call that one u. And we're projecting this gradient onto u. And what we're concerned with is how much impact or what kind of projection that gradient vector has on the vector u. We're not looking for, if you remember back to chapter 9, we're not looking for the vector projection. We don't really care what this green vector is. We care what the length is. So we're concerned with the length of that green projection because that's what impact the gradient has on the unit vector itself. Okay, so the gradient vector is really kind of like the behavior of the surface at the particular point. We're looking more specifically at how does the surface behave in the direction that we want. So we're going to project it into the direction that we want. Now, if you remember the formula was the component of the gradient vector onto u, which was equal to the gradient vector dotted with u divided by the magnitude of u. Now remember, the unit vector that we're dealing with is truly a length 1, which means that the magnitude of it is, of course, 1. And so that's where we get, that's where we get the formula, the gradient vector dotted with u, and that's exactly where the directional derivative comes from. So how do we come up with the directional derivative formula? It really comes from the projection of the gradient onto u. And why do we need u to be a unit vector? It's because based on our formula, when we're looking at the component form, is that this relationship of where we're projecting it onto must be a unit vector in the form of that dot product. So that's kind of where it comes from. I hope that makes a little bit of sense. But either way, this gradient is a very important vector that we're going to use a lot in the next handful of sections and chapters. But your directional derivative really should be thought of as the gradient times u. Okay, now I'm going to explain one more pretty important concept with the gradient, and that is that when we analyze the gradient and we look at level curves or the contour curves of a particular surface, the gradient is actually going to show us the greatest rate of change along that particular surface. So let me just, I guess, draw just a quick diagram and explain why this is. So let's say that we have, you can just add this if you'd like. So let's say we have a surface, and I'm just simply projecting the surface onto the XY plane. So this surface is like hovering over the page, let's pretend. And so I'm just looking at the shadow that it casts on the XY plane. Now, if there's a point that we're analyzing, let's say the point is at x sub 0, y sub 0. And I have, for example, my gradient vector, let's say that points in this direction. And I have my unit vector, let's say I'm trying to analyze it in that particular direction. We have the relationship of the directional derivative, which is, like we just talked about, the dot product now between the gradient and the unit vector, okay, so the gradient vector. Based on your dot product formula that we learned in chapter 9, it's the same thing as the magnitude of the gradient multiplied by the magnitude of the unit vector multiplied by the cosine of the angle that's formed in between them, okay? So I'm just using the dot product formula and both methods of it, the one where it's just simply the dot product between two vectors, and the second one where it uses the magnitudes as well as the angle. Now we know that the value of the magnitude of u is of course 1, because by definition it's a unit vector. And so what happens to our directional derivative formula is that it's the magnitude of the gradient vector multiplied by the cosine of the angle between those two vectors. Now, if we're trying to figure out the maximum, or in turn the minimum, of the gradient vector, we have to think about what happens with the cosine of your angle. And we know that the cosine of any angle itself is going to be in between -1 and 1. So let's say that we were trying to, for example, maximize the directional derivative. That would happen, or that would occur, when cosine of the angle is its largest value, which would be 1. Therefore, the maximum of a particular directional derivative would be the magnitude of the gradient. And again, that's because cosine of the angle would need to be 1 in order to maximize that equation. If we're looking for the minimum directional derivative, that would then be the opposite, because cosine of the angle would be -1. And if cosine of the angle is -1, then you would have negative of the magnitude of the gradient vector itself. Okay, now the significance of this, I think, will start to kind of sink in as we work through this, but this is a really important concept as we analyze a particular surface and the impact the gradient has on that particular surface. Now let's go back up to these diagrams for a minute. So we know that if we look at any particular point, the maximum rate of change at that particular point will be the magnitude of the gradient vector in the direction of u. If we were to think about, for example, if I take the one on the right side, if we look at these contour curves or these level curves of this particular surface, and we think about, in terms of, if we take a point, let's say, and we look at, okay, where would we move to increase the fastest along a particular surface? The answer would be that we would want to get to the next contour as quickly as we possibly could. Okay, that means that the gradient vector will be perpendicular to any level curve initially. Now keep in mind that, when you look at a level curve of a surface, that level curve could be written in increments of 100, it could be written in increments of 20, or whatever the case is. We could have multiple increments, and so we really need to analyze that at every single point on a particular surface. But if you're analyzing, for example, a single point on a level curve, the gradient will be perpendicular at that particular moment. Now, as you change location, as you travel along a surface, obviously the position of where the gradient is and the direction in which it points is going to change, because a surface will change unless it's completely symmetric. It's going to change in how the motion and the steepness of the curve changes. So, for example, if you're sitting at the bottom of a mountain and you're trying to get to the top as fast as you possibly can, it doesn't mean you're going to walk in exactly a straight path. You're going to probably go in slightly different ways, just because as you move along a mountain, one path is going to get steeper in a particular direction than another one based on the gradient and how the surface changes. So again, the idea here is that the gradient vector at any particular point on any particular level curve at that moment is going to be perpendicular to that level curve. And the reason for all of that is that we have this idea that the gradients, or the directional derivative's maximum, is the magnitude of that gradient, and therefore the gradient is going to dictate the fastest rate of change, or the largest rate of change at that particular moment. Okay, let's move on and look at the next example. So with example 3, we're going to evaluate the gradient vector. So the gradient vector is simply just the partial derivatives as components of the vector. So in this case, the gradient vector would be cosine of x plus y e to the xy, because of the chain rule. And then we have x e to the xy as the second component. And we're going to analyze the gradient at two particular points. So we're going to let x be 0 and y be 1. And so we get a gradient vector of 2, 0. That's just a quick practice on just simply calculating the gradient itself. Okay, let's try example 4. So we're going to find the directional derivative at the point 2, -1 in the direction of this particular vector. So keep in mind we need a unit vector. So our first step is to calculate the magnitude of v in order to make sure that this vector is going to be a unit vector. So we have 2 squared plus 5 squared, and that gives us the square root of 29. So our unit vector will be 1 over square root 29 multiplied by 2, 5. You could distribute that. That would be totally fine. You could write that a variety of ways. I also need in this the gradient vector because, again, that's part of my directional derivative calculation. So my gradient vector is 2xy cubed and 3x squared y squared minus 4. And then I want to make sure to calculate the gradient at the correct point, which is 2, -1. So we get a gradient vector of -4, 8. So again, if we're, just to kind of reiterate on the last page, if we're at the point 2, -1, and I want to know in which direction is the surface changing the fastest, the answer would be in the direction of the gradient. Okay, because the gradient, that magnitude and that direction is going to allow me to increase the fastest at that moment. Now in this case, I'm going in a different direction because the vector we're analyzing is not the same vector as the gradient. So the gradient is -4, 8. I'm going in this direction, 1 over square root 29, 2, 5. So I'm not going in the same direction as the gradient, which means that the rate of change is going to be less than it would be if I would go in the direction of the gradient. We're going to calculate the directional derivative, given all of the information we have now at 2, -1. And remember, that's going to be the gradient vector dotted with the unit vector, which is 1 over 29 times 2, 5, or of 2, 5. And so we're just going to multiply our parts. I'm going to take the 1 over square root 29 and pull that to the front. -4 times 2 is -8, and 8 times 5 is 40. And so we get a rate of change of 32 divided by square root 29. And again, that's going to be our rate of change in the direction of that vector v that we were given. Okay, let's try one more example on the next page. All right, this last example before we get into some of the maximum and minimum stuff is going to be just the same idea, except we're going to increase our variables. The gradient itself is just going to add another partial derivative, so it's the partial derivative with respect to z. Other than that, it really doesn't change. The formula is consistent, and so we're just going to try example 5, given our additional variable. So we have f of x, y, z. We want to find the gradient and then the directional derivative at a point. So again, the first thing we'll do is to calculate the gradient, which is our list of partial derivatives. So the partial with respect to x, the partial with respect to y, and then the partial with respect to z. All right, so there's our general gradient vector. We want to analyze the gradient vector at the point 1, 3, 0. So a lot of stuff is going to cancel here because sine of 0 is 0. So we have the first term is 0. Since z is 0, the second term happens to be 0. And then the third term is going to be 3. So there's our gradient vector. So again, to reiterate, if you are at the point 1, 3, 0 at this particular surface, the greatest change will occur in the direction of the gradient. However, in this case, we are going to go in a different direction. We're going to go in the direction of v. So again, I need to make this a unit vector. So I have the square root of 1 squared plus 2 squared plus -1 squared. So I get the square root of 6. So my unit vector that I'm analyzing, or the direction in which I'm traveling, is 1 over root 6, and then 1, 2, -1 for my vector. So I think I have everything I need. Now we're just going to calculate the directional derivative in the direction, or the directional derivative at the point 1, 3, 0. So I have my gradient vector, which is 0, 0, 3, and I'm going to dot that with my unit vector. So we calculate each of our components. A lot of them cancel because of the zeros, and we're left with negative 3 over root 6. So that's the rate of change in that particular direction. Okay, that's done. That's it for the first video. The next one will be on the maximum and minimum values, which I've already kind of hinted at along with the gradient. Thank you.